everybody. In this video today I'm going to be talking about one new topic, which is data fitting. Data fitting is one of the things that people use a lot, especially those who are doing experimental work and they have experimental data and they want to do some fitting on it. And I'll discuss briefly what do we mean by fitting. So let's assume that you have experimental data relating X to Y, where X and Y are two variables. Could be temperature, concentration, pressure, it could be time, could be volume, velocity, anything. And you have some experimental data that relates these two, like tabulated data like this, and you were able to plot these data this way. You have Y here, you have X here, and you have some scattered points here, and you want to get something out of these points. Anything you need to get out of these points to be helpful in the future. And what you actually need to get from this table is that you want to expect what is the relation between these two variables. How does it look like? Does it look like Y equals AX plus B? Or does it look like Y equals AX squared plus B? Or you can have it Y equals ln X. I don't know. This is one thing that you don't know, and you want to find out what relation is the best relation that describes these data. And actually you need to do this for many reasons, but the most famous reason is that you want to know or you want to be able to predict the value of Y at any value of X without the need of doing more experimental data. So you did experimental data, you now know how the behavior goes, and then you want to predict in the future how would this variable behave with the change of the other independent variable. So this is one thing, or one case that we need to do this fitting. So this is called fitting, is to see which equation describes this pattern the best. One other thing that we need fitting in is that in other cases you might have some experimental data, and you know, for instance, that we have it a lot in kinetics, that there is an equation that looks like this, K naught E exponential of minus E over RT. So this is a very famous equation. It's called Arrhenius equation. This is K. And this relates the rate constant, or the rate of reaction to the Arrhenius constant and the activation energy. And in this case, you know exactly that the equation looks like this. You know that, and you have some experimental data relating temperature to the K, and you have already these data known. But in this case, you know how the equation looks like. So what you're actually trying to get from this fitting is that you want to use this experimental data to get the values of K naught and the values of E. Okay, so either like what we have here, you don't know how the equation looks like, or like in this case, you know how the equation looks like and you want to get the variables. And of course in this case you would get the variables, but in this case you don't know the variables, what are the variables, but here you know how the equation looks like, and you just need to get the variables. So there are many other reasons you would go for fitting, but these are the main most famous reasons, you could say. So let's see an example and see how Matlab could help us with this. So we have now an Excel file that has this data. It's just any two random variables, A and B. We can zoom in. We have it from 1 till 10, and you have here 46 points from 1 to 10, and you have the corresponding values of B. One thing we will learn today is how to import these data into Matlab. So we have Matlab here, and you don't want to copy all this type all these values by copying and pasting or doing all these kind of random stuff. So I have this file in a folder called lecture examples, in this subfolder, in another folder, and so this is the path of the folder. So you have to make sure first that this is the current folder that you're opening, and you would see it simply here. The file is called linear fitting example. Okay. So because what we're going to do now is to open this Excel file and get the data, and Matlab will search in the files in the current folder, not any folder in your computer. So the command that we're using now, I would call it data. It's called XLS, which means Excel read. Okay, so what you are asking Matlab to do is to read the data that you're opening, and you need to enter first the file name. It's called linear fitting example.xlsx, linear fitting example.xlsx, and now we want to add the sheet number, so it's sheet 1. 1, and finally the cells. So you want to have it from cell A2 to B47, A2 to B47. And when you press enter, it will take a little bit of time. It's busy now. Sometimes it takes more or less time depending on the processing of this order. So what's doing now, it's opening the Excel file and that sheet and then getting the data. And this is exactly what we had in the Excel file from 1 to 10, and we have it 46 by 2. And now I can say that A equals data, all the rows, but column number 1, and B would be data, all rows, and column number 2. So we have now the variables as A and B, and we want to do the fitting using these two data. So it's one nice thing to learn is how to get data from Excel file. This is pretty nice example. And now let's see how we can do the fitting. In this video, we're going to see what's called the fitting app or data fitting app. If you open this ribbon here, it's called apps. You'll find many things here. There's things that are related to math and statistics. There are control systems, signal processing. There are many other things that I personally didn't use, almost all of them, but they will be of interest to those who are working on stuff that are related. So you can look at them closely if you have something that you see it's interesting. But what we need to see today is the curve fitting app, which is actually in math and statistics. So if we do this app, we will open a new window. It's taking a little bit of time. And here's the window. Let's just make it like this. Okay, so this is how the window looks like. It asks you pretty simple questions. What is the source of X data, and what is the source of Y data? And this is all what you need to do actually. It's now should be, yeah, it will. It's kind of slow now, but this is what it's gonna do now. It's using the data to do the fitting. And actually you need to give it more information, so you need to let it know what is the kind of equation. Is it linear fitting? Is it polynomial? Is it power, rational, sum of signs? There are very powerful curve fitting app actually, and that's why you will find some I don't know what are these equations, might be famous equations that I do not know, but there are many equations that you can use. In Excel, if you remember when we did this curve fitting before, what we used to do is to plot the data. So first we have to insert scatter, and this is something that we do not need to do in Matlab, and then to right click here and then add trend line. And when you add trend line, you would find some very limited options. Is it linear, exponential, logarithmic, polynomial, power, and moving average was just smoothing the line. It's not or the data is not fitting actually. And polynomial you can choose, is it first order, second order, third order, whatever. And we would when we can display the equation and display what's called the R square, which is the goodness of fit. As it goes to 1, it's a good fit. As it goes to 0, it's a bad fit. And this is how we did it. But if you have something that's out of this 4 equations not included in this, we had to do the least square fitting, which is something that we mentioned before in Excel series. But here you can find a lot of equations that are they're very good equations actually, might be of interest to many other people. Here we're interested in linear fitting, and as you see, even the linear fit here looks very weird. It has sine and x minus pi, so it's not actually what we call linear, and that's why when I want to do linear fitting, I make it polynomial and make it of first degree. And here you can see everything. You have the r squared 0.9403, which is, let's make it linear again here, it's 0.9403, and you have y equal 10.866x minus 14.869, and these are the values 10.87 and negative 14.87. So it's giving you the equation, how it looks like. It doesn't give you the equation with the numbers in it, it just gives you the equation and the parameters in the bottom, which is the same thing. So you have these two numbers, and you have the r square. We have here the sum of square of errors. We will talk about this later. Everything is done. You don't need to do anything else. One more thing that is very powerful in Matlab than in Excel, if you have an equation that does not have is not included in one of these equations. Let's say you have another equation. So what are you gonna do? In Excel, we said there's no way to do it with fitting. You have to go for linear square. Root mean square. Least square method. I'm sorry, the least square method, which we discussed before in Excel. But here you can see that in Matlab it's different. So we have this example here of x and y, and we have the equation y equals ax plus b over x plus c, which is not included in any of the equations that we mentioned before. So we can first get these data. And then do the fitting. So we will get new data. I will call it data 2. It's XLS read. The file is called least square method Excel file.xlsx, and I need to get the cells from A4 to B16, A4 to B16, and here we have the data starting from 3.4 ending in 4.67 exactly. So we'll have C equals data to all the rows and column number 1, and D equals data to all the rows and column number 2. So now we have C and D, 13 columns by 1 row. You can now open this, and you can open a new fitting actually here. I can make it non-linear if you want to name it something, and you can choose the X source and the Y source, which is going to be C and D. And we'll now go to the tricky part. So you don't have the equation in one of these equations here, so you can do what's called the custom equation. And the custom equation, you can enter the equation that you want to do the fitting on, whatever the equation is. It doesn't need to be included there. You can write any kind of equation that you want, which is it's great. So you can make it a multiplied by x, and you see here it's y as a function of x, so the variable is x. Ax plus b over x plus c, and you will see here now he said you have 3 coefficients. The software now understands that you have 3 coefficients from just typing this, and it's done with the fitting. It says that it's A is 0.02435, B equals 26.73, C equals 1.568, R squared equal 0.9968. If we go back to our Excel sheet where we did the least square fitting, you'd find that these 3 numbers are the same. R squared is the same, but if you revise this file, For this video, you'd see how much time was spent to do all these calculations. You had to calculate y and then y squared and what's called y calculated based on these three, and the difference and the sum square of the errors and all these kind of calculations just to get these three numbers and the r squared, and we just got them in less than few seconds. It's just a click of a mouse with just entering the equation, everything is done. So it's actually a very, very great tool that you can use to do the data fitting using Matlab without spending much time on doing the least square method or doing the other calculations. So in the next video we'll talk about doing the least square fitting in Matlab. It's way easier, even if you want to do this with the least square method in Matlab, it's going to be way easier than doing this in Excel. It's just a command that you enter, and we'll talk about this next time. And I'll see you then. Goodbye.